development of getting the spin dynamics into gravitational classical scattering amplitudes.
Yeah.
Please.
Thanks. I was going to be like a very formal seminar, so probably can make it a little bit more informal. And it's going to be basically trying to understand the binary dynamics for black hole with spins at higher orders in spin and higher orders in the post-Newtonian expansion. But we try to avoid as much as possible the loop computations and try to recycle information that is there from gravitational wave computations. So in particular from cell force analysis and the new computations from gravitational Compton amplitudes from solutions of the Tucholsky equation. So I'm going to divide the seminar in two parts. And it's going to be based in a couple of papers. So the first part of the talk is based in a paper that appeared last week in the archive, and we wrote with Mohamed Khalil, which is a postdoc at the Perimeter Institute, Matteo Sergola, who is a postdoc at Saclay with me, Chris Kavanagh, and Justin Vines, who you have heard of. And so for the first part of the talk, we are going to try to understand the post-Newtonian dynamics for spinning aligned spin binary system at 5.5 pn and 6 pn orders at spin to the 3 and spin 4 couplings. And then the second part, we're going to mostly talk about this second paper that appeared last year with some people from CISA, Giulio Bonelli, Cristoforo Iosa, and Alessandro Tanzini, and Zihan, who is a student in Princeton. And it's about taking the advantage that the equation for the perturbation theory, black hole perturbation theory, appear in other contexts in physics, such as conformal field theories and gauge theories. So the new approach to solving black hole perturbation theory equations will naturally give us like some imprints on in this case the Compton amplitude, which is like one of the building blocks for the two-body problem. So I'm gonna understand a little bit better the properties of this Compton amplitude based on the properties of the functions that appear in the solutions of the Tucholsky equation from this viewpoint. So this slide you have seen. So we heard from Rafael yesterday that as we transition from the observational to the precision from theory in gravitational wave measurements, we need to develop better and better gravitational wave templates, right? And those gravitational wave templates should be fast to evaluate, right? Because we're going to have tons of events in the future. And also they should keep as much information as possible about the binary system because we want to separate true GR effects from possible deviation from general relativity. So it's very important that we include as much information about the binary system in Einstein gravity and then parameterize the possible deviations in some other form. On the way, there could be also some hidden structures that could arise that will probably help us, access computation where it is more difficult to do the computations, like based on structures and symmetries, like, for instance, when you introduce a spin, there are some kind of symmetries appearing, like spin shift symmetries, which are still like, allows you to do like resumations of the spins, like parts of the answer that otherwise you will have to work out. So the philosophy of this talk is try to use to recycle as much information as possible to try to compute the observables in the binary systems without doing the computation. So as far as you have like some expansion parameter in the two-body problem, you can do computations, like for instance, in the scattering scenario, you can do like a weak field expansion. And on top of that, you can re-expand in velocities, that's what's called the post-Newtonian expansion, or you could have, say, a very heavy black hole and a very small black hole and do computation with small mass expansion. And it's natural that all of these expansion will intersect somewhere, right? So that will help you to prove the computation that you do in the intersection region. But also the intersection region can give you information from some given observables computed to compute new observables in that intersection region without having to do the computation. So that's basically the philosophy of the Tutti Frutti method introduced by Bini, Tambur, and Geralikov, in which basically you do compute observables in the two-body problem based mostly on information from gravitational self-force, which people have computed analytically to very high orders in the post-Newtonian expansion. So we'll use that philosophy to approach the spin Q and spin 4 contribution that we are interested in this talk. And in principle, like as I'm telling you, like people have done computations to very, very high orders in the post-Newtonian expansion. And you could say, okay, why don't you just continue higher orders in spin 2 from that, those computations? But there is the usual problem that you start having the appearance of non-rational functions of the spin, and it's difficult to separate the spin multiple structure from those functions. So we will need a new ingredient, which comes from matching the Compton amplitude to wave perturbations of the Tucholsky equation. And this matching comes naturally written in the spin multiple expansion. So it's easier to introduce these higher spin contributions in this way. And then you can try to compute new observables and see if you agree with the old ones and produce new ones. Yes. Yeah. So it was very sketchy, but it's basically an expansion. The post-Mikowskian expansion is an expansion of, in the two-body problem, you have two scales, say the Schwarzschild radius of the two guys, and then the separation between the two guys. So post-Mikowskian expansion is a separation of, it's an expansion in the separation of the black hole as compared to the sizes of the black hole. But roughly speaking, it's say when you do QFT approach, it's just an expansion in G. Yeah, so it's like a radius as compared to the separation of the two guys. Yes. So we'll make it more concrete later on. So this is what we have in mind. So we want to, in this table, which is say the contributions in the binary dynamic, the dynamics for the binary Hamiltonian, we're going to have a couple of black holes with spin. They could have, in principle, comparable masses. And we want to understand how to write a Hamiltonian at the spin 3 and spin 4 contribution, which are these couple of guys, at the 5.5 pn and 6 pn contributions. So, and then based on Tucholsky gravitational wave scattering information, we'll address this other part of the problem. The two are spinning, so it could be like one Kerr black hole and then a small guy with spin 2. S is the spin, so So it's basically, S is like spin multiple expansion. So S to the 0 is just, you have a Schwarzschild black hole. S to the 1, you have an object with a spin dipole structure, and so on and so forth. Yes. S is supposed to be, it captures both. Either S to the 0 would be the 2 0. S to the 1 would be either of the two having a spin dipole. S to the 2 would be the two having spin quadrupole or spin dipole interactions.
S2 means S1 squared, S1 is 2, S2 squared.
Yeah. All of the possible combinations. Yeah. So yes. Yeah. The eccentricity can parameterize like a very open ellipse or a very, very close to a circle. So it's just a parameter that can vary softly, right? No. I'm going to talk about using bounded or unbounded information to fix the Hamiltonian. And once you have that Hamiltonian, then you can compute observables for whatever orbits you want, either closed or bound, eccentric or not eccentric orbits. So that's the idea. If you were to do the honest computation to fix this couple of guys, you would have to do a one-loop computation for these guys, and then a two-loop computations for these guys, which is probably not very difficult to do, but we're going to take advantage of the information that is already out there for not doing those computations. So let me go to the first part. So okay, sorry. Thanks. So let me review what is this tutti frutti approach. So it was introduced by Damour, Geraldikov, and Bini. And it started with a very simple observation. So let's consider that we are scattering two Schwarzschild black holes. So they are separated by the impact parameter V. And then you want to compute, say, for instance, the scattering angle in a post-Minkowskian expansion, meaning an expansion probably for GM over V, right? So, and this M can be either the mass of the one or the mass of the other. And so in general, this is going to have this series form with some functions. And these functions, they can be only functions of the only dimensionless parameter appearing in the process, which is the relative velocity between the two guys, right? So, but then the observation is the following. So if you translate this series into this new, which is the symmetric mass ratio between the two black holes and the total mass, you realize that up to third order in the post-Minkowskian expansion, this symmetric mass ratio can enter at most linear in the result, which basically tells you that it doesn't really matter where these two black holes, they have comparable masses or not. Up to the third order in the post-Minkowskian expansion, you can fully fix the scattering angle based only up to one order in the gravitational self-force computation, meaning leading a linear order in nu. So gamma here is the Lorentz factor, which is basically the relative velocity between the two guys. So that's going to be our observation. So we're going to stop at 3 p.m. order. But in general, you could continue if you wanted. It follows from dimensional analysis, right? Like you just translate this expansion into these variables, and in this nu appears just linear in there. Like there is no nu square at that order. Oh yeah, of course. You impose the exchange between the two guys. Yeah. Okay, so the idea is to try to fix these functions without doing the computations, and in principle, all of the 1SF information available in the literature is mostly being doing for black holes going in bounded orbits. So for those, you have to do the, on top of the weak field expansion, you have to do a small velocity expansion for that case. So then, well, you can do that in your scattering angle ansatz, because basically you can re-expand these functions in powers of velocity, and all of the coefficients accompanying this expansion are going to be pure numbers that you need to fix somehow, either doing the full computation or using gravitational self-force information to fix those coefficients. So once you have your scattering angle parameterized in this way, then you can translate that new dependence into an ansatz for the Hamiltonian of the two-body guy. And then that ansatz of the Hamiltonian is going to have some free parameters, some free coefficients that you can translate into the coefficients of the scattering angle by imposing that the scattering angle that you compute from such Hamiltonian is exactly equal to the scattering angle ansatz that you wrote, right? But then, with that Hamiltonian, you can now use 1SF for information, because from that Hamiltonian, you can compute other observables like redshift or spin precession frequency, which are the kind of observable that gravitational self-force people are computed. And then you match at every order in the post-Newtonian, and we are interested in spin expansion to fix to fully fix the Hamiltonian. So once you have fully fixed the Hamiltonian, then you can use that Hamiltonian to compute any observable you want, right? And in particular, we're going to see that we can, to the spin 3 and spin 4, which we are interested in, we can fix all of the full Hamiltonian for information from black holes going on circular orbits, right? So then, once I have fixed that Hamiltonian, I can compute the observable for black hole going in eccentric orbits. And one of the main results of this paper is that we have computed those observables without having to do an eccentricity expansion. So they are valid for any kind of orbit, if you like. At this order, they don't appear, so I'm just fine. Those ones are a little bit more difficult, and you and Rafael care about those ones. For me, not yet. Yeah, this is purely the conservative contribution to the. Well, radiative effects will show up at higher orders in the post-Newtonian expansion, so we're fine. So okay, so let me tell you how to fix these coefficients from gravitational self-force information. So we want to introduce a spin in the game, right? So the observation for the scattering. Yes, but I'm going to tell you how to introduce a spin in the Hamiltonian, right? I will show you how the Hamiltonian looks like in the next slide, because I'm just doing the analog of the scalar case, right? I will write an answer for the scattering angle for the spinning case, and then I'll match that to a spinning Hamiltonian, and I'll show you exactly what the Hamiltonian looks like. So when you have a spin, you have an additional scale with which you can play it, which is the radius of the ring singularity of the black holes. So you can expand also in powers of A over B, where B is the impact parameter. That's what people call the spin multiple expansion. And we are interested to go into 5.5 order in the post-Newtonian expansion. That will imply us to do a velocity expansion up to this power, which is not very important for us. But what is important is that you include up to third order in the spin multiple expansion effects in there, and linear order in the mass ratio contributions. When you have a spin, there is also contribution from the asymmetric mass ratio because of the symmetry exchange between the two bodies. And up this order, you have 5 unknown coefficients at 5.5 pn order. So this F30, G30, and this H3S0, and the other ones. And we want to find what are those numbers. So here's the Hamiltonian. So for the Hamiltonian, you parameterize in the following way. So you use the 0 pm contribution. As the 0 pm contribution, you can just use the effective one-body Hamiltonian, which you can further expand in velocities if you like. So it's expansion in P. There is then the tower of spin multiple contributions. So the spin 0 contributions, linear in the mass ratio, and further expanded in velocities, with some free coefficients, G11, G12, and so on and so forth, which you can fix. And then you can add all of the towers of spin multiple moments. So this is for the all powers. No. Well, those ones for us are not really important. We really care about this part. That's just for completeness when you try to match the gravitational self-force computation, and then you ensure that you also match the spinless contributions. Then you have to use that one to match the higher powers in B. But in principle, we are just interested in this part. This is the important part of the Hamiltonian. So we are expanding both in spin and in velocities. So yeah, this is supposed to be small. No, that's the 0 pm. This comes with one. Yes. No, these are not just this expansion there. Exactly, this is G equal to 0. So these have G contributions, but those can be fixed. So those ones people have actually computed, and You just put them for completeness. But the important ones are this one. These are the new ones. Yeah, exactly. Up to certain order in the PM expansion, you do know them. Up to G4, right? The people are doing now the for loop computation, which still, but these ones before G4, they are known. So I will parameterize the scattering angle, the spin dependence in the scattering angle in this sort of vector of spins. So basically, at every ordinate spin multiple expansion, I'm going to add more powers of spin in this sort of vector made of spins. And I'm going to have also on top of that spin multiple expansion in powers of P with some free coefficients. And those free coefficients are going to be basically multiplying as a spin multiple operator of the form. Let's say you have the spin 1 to the L, the spin 2 to the M, and certain powers of velocity to compensate for the post-Newtonian expansion. So in the end of the day, by imposing that the scattering angle that you compute from this Hamiltonian is equal to the scattering angle that you wrote for your ansatz, then you will be able to translate these free coefficients in the Hamiltonian to the coefficients in the scattering angle. Oh yeah, that's very important. So I'm going to be mostly talking about aligned spin black holes. So presumably you can do like misaligned spin, the computation a little bit more complicated. And also because like most of the gravitational self-force results have been done for aligned spins. So then you have to include like spin precession effects, which are not clear how to introduce, at least in those approaches. Okay, so we want to find those alpha coefficients or equivalent those F coefficients. And so how do you do that? Well, you wanna, they are aligned with the angular momentum of the plane, of the system. So it's, yeah, it happens in a plane. Okay, so we want to fix those guys. And to fix those guys, well, I have to compute observables that have been computed in gravitational self-force physics. And people usually compute two observables, redshift and spin precession frequencies, which would result for circular orbits available out there. So we want to compute those ones from the Hamiltonian, and you can just use the first law of the aligned spin circular orbit binary mechanic by Lettier, which basically says like once you have your Hamiltonian, you compute the system free energy and take derivatives with either the masses of the spin of the black holes, and that gives you your observable. So those are the observables that we will match then to the computation of gravitational self-force. So this is the result. I'm not going to show you how to compute the observable, but what is the final result for the free coefficient that you have in your scattering angle? So I was telling you the scattering angle has nu to the 0 and nu to the 1 contributions. So the nu to the 0 contributions can be fixed completely from zero order self-force inputs. So basically, if you take a spinning test guy moving around a Kerr black hole and solve for that geodesic motion, you can then compute completely fix those coefficients that come without any powers of the mass ratio. So these are solutions of spin 3, this couple of guys. This also includes solutions of spin 4 if I wrote the complete spin to the 4 ansatz here, which I didn't. But it's analog. It's very easy to do it. And then you have the ones that come linear in U. And for the ones that come linear in U, you can use the result from Chris and collaborator, Donato Bini and collaborators, for a small spinning mass moving around a Kerr black hole, right? So, and at spin to the 3, you get a couple of constraints of these H coefficients. So these H coefficients are the ones that come linear in the mass ratio. And those equations are enough to solve for the unknown, for all of the unknown at spin to the 3. At spin to the 4, on the other hand, which I didn't put the angles I'm saying, you also get some constraint, but there is one coefficient that you cannot find. And that coefficient will be the coefficient accompanying 2 powers of spin in one of the guys and then 2 powers of spin in the other guy. So for obtaining that information, you will have to do one self-force computation in which you have a secondary object with a spin quadrupole structure, which people haven't done yet. So that one is still unknown. No, because of the linear, we are stopping that up to the linear or 1SF contributions, so it's fine. These coefficients are fine. You will have to introduce additional operators in your scattering angle that goes like nu square, and then all the possible spin multiple structure for those operators. No. The coefficients. Well, the fact that these are integers or well, they could be in general rationals. Yeah, but yeah, that wouldn't change, I think. At lower orders in spin, these are fine. At higher orders in spin, you will get in general functions of the Kerr spin parameter. We're going to see that now. But at lower orders in spin, you can explain that basically by the fact that the post-Minkowskian expansion and the spin multiple expansion, they never mix. When they start mixing, then things start to become complicated, and it's not really clear how to separate those. So this is what we have so far. So we have fully fixed those free coefficients on the scattering angle, or equivalently the free coefficients in the Hamiltonian ansatz at the spin to the 3 and spin to the 4 order at the next to lean order in the post-Minkowskian expansion. Oh, these guys? I don't know. Probably you can put a. Yeah, I didn't think of well, those. Okay, let me see. What are the factors of them? Are the G's and the F, for instance? The H, they are not. So that will be like a factor of them for the ones that do not depend on nu. Yeah, I cannot really spot it where that could be coming from. I can think of, I didn't stop thinking of what were the numbers. But yeah, I'll try to think of that. Yeah, I think the sign is just what comes from the computation. Not well. Some of them they come accompanying the symmetric mass ratio, the nu, but some of them come accompanying the anti-symmetric mass ratio, which is like kind of like will have like a negative sign somewhere. So I'm not surprised that they come with plus and minus signs. So that's it for the spin to the 3 and spin to the 4 contribution for the Hamiltonian. In principle, you could continue the game for the spin to the 5 and spin to the 6 contribution at the 6.5 pn, for instance. The problem when you want to use the gravitational self-force information is that at this precise order in spin, you start to see those non-rational functions of the spin parameters of the Kerr black hole. So say, for instance, if you wrote an ansatz for your scattering angle at that order, you're going to have a couple of free coefficients. And you want to match those coefficients to the gravitational self-force coefficients. And one prescription, you could say, okay, maybe I can just match the spin to the 5 guy with the spin to the 5 guy, and then that will give me that number. The problem is that this rational function of a spin, they have identities that allows you to reabsorb powers of a spin inside the argument of those polygammas. So it's not a very well defined prescription to match those coefficients. In addition, since this is a result that was computed for circular orbits and aligned spin, it has hidden totally the spin multiple expansion that was there at the beginning of the computation. So it's difficult to know what is really a spin to the 5, what is spin to the 3, what is spin to the 1, because you can always, collect powers of chi inside those kappas, inside those polygamma functions. So it's very difficult by just comparing this guy. This is a self-forced result. So this is the redshift evaluated at the 6.5 PN order, and I just took the eccentricity square contribution, for instance, and this is what it looks like. So this was computed last. Yes, it's only the spin of the big one, and then the other one doesn't have a spin. So which is this? One spin in the one, or the symmetrized part? UP is just like a post-Newtonian parameter. It's like a velocity parameter, if you want. It's not really important. It's just saying that I'm evaluating exactly at the post-Newtonian order that I need to when I want to compare the scattering angle computation. UPS is like the V parameter, like the V over C expansion, if you like. No, I think it's equivalent. So I just want to take the sorry, no, UP doesn't blow up. I'm just.
V over C, I think I'm expanding V over C being small, near 0.
Yes.
UP, I expand near UP small.
No, UP is proportional to V over C.
So that means I should expand near UP small, proportional to V over C.
Yes.
So then log UP is not well defined.
Because those are non-local contributions. Yes.
So everything should be multiplied by UP.
Yeah. This is evaluated at UP to the 15 over 2. So that's multiplying that factor. Okay, anyways, you cannot fix those guys just by comparing to this result. So you need to find.
I just want to understand what that means. So you don't understand it, or it means that the term in the expansion, which goes like UP to the 15 over 2 times log UP. You really
Yes, there is a term that goes like that. I can tell you where this come from in the coming slides when you do black hole perturbation theory computations, but there is several sources where this can come from. So this basically come from logarithms of the velocity appearing when you do the Feynman integrals, if you want. Okay. So I cannot just use the tutti frutti method in the usual way as designed. So I have to use some other information, and that's where the Compton information comes from. So I cannot avoid to do the one loop computation for this guy, but it's a very simple computation. So I'm just going to target these couple of guys. For computing this couple of guys, I just need to compute like a one loop triangle diagram in there where you have two building blocks. And the two building blocks are the usual 3-point amplitude for the Kerr black hole and the Compton amplitude for perturbations, gravitational wave perturbations of the Kerr black hole. So if you compute that diagram, then that diagram gives you directly the scattering angle, And then again, you can relate to the Hamiltonian and compute observables. So you're gonna have to write an ansatz to what such a Compton amplitude looks like. Either you have an effective field theory for doing that, you can write an on-shell ansatz. The important thing is that you're gonna have free coefficients. And those free coefficients, we have like a far zone contribution, which is where the black hole looks roughly like a point particle, and a near zone contribution, where the black hole where these coefficients start to capture the finite size effects from perturbing that black hole. So we're going to be able to capture all of those when you match to black hole perturbation theory solutions. So let us compute those building blocks. The 3-point amplitude is very simple. It's just you take the Kerr metric, you expand the leading order in the post-Minkowskian expansion, meaning leading order in Gm over R. But you keep all orders in the spin multiple expansion, meaning all orders in A over R. So that's the usual exponential that you can match into a 3-point amplitude. We know that from a very long time ago. And then the other one you have to solve for the perturbations of the Kerr black hole. Spin 2 perturbations of the Kerr black hole, which will allow you to extract a gravitational Compton amplitude. So you have to solve the Tukhowsky equation. And the Tukhowsky equation is a second-order differential equation for the Tukhowsky scalar. It takes different values depending on the spin of the perturbation. We are interested in the spin 2 perturbations, which are gravitational wave perturbations. And this can be separated thanks to the existence of the separation constant, which is like the angular eigenvalues. And the way you need to think of that separation constant is, roughly speaking, like the wavy analog of the Carter constant when you are putting a spinning test guy moving around the Kerr black hole, so that you can the Carter constant ensures that you can integrate that system. So roughly speaking, the separation constant does the same job, but in the wave scattering scenario. So the usual way of solving for the radial equation, the radial equation will satisfy differential equation. The radial function will satisfy the differential equation, and people have done it from the 90s using the method of Manu, Suzuki, and Takasugi, in which you expand the solution for the radial equation into different regions. So for instance, in the near region, you can do an expansion around the hypergeometric equations, and the far region, you can do an expansion into Coulomb functions, which have these ones converge here, but not here, and this one's converge here, but not here. And then you can glue the two together somewhere in the middle, which will give you a 3-term recursion relation for these free coefficients, these AN coefficients. But you still have to do infinite sums of those. And you cannot find closed solution yet because those are Hoyne type of differential equations which do not have a closed solution yet. So Hoyne type of differential equations are second-order differential equations with 4 singularities, 4 regular singularities, 0, 1, some point A, and infinity. And actually, the differential equation that you get from doing the perturbations of the Kerr black hole is not the Hoyne differential equation, is the confluent limit of that one, where you take 2 of the regular singularity and collide them and form an irregular singularity. So the confluent Hoyne equation has 2 regular singularity, one at 0 and 1, which is the position of the outer and the inner horizon of the black hole, and one irregular singularity at infinity. So for instance, if you take the Tukhowsky equation and go to the static limit, you recover the hypergeometric equation. That's why you can sort of do expansions around the hypergeometric equation near the horizon, but not at infinity. The Coulomb one has a regular singularity at 0 and a regular singularity at infinity, so that's why you can use that one at infinity. In general, when you do perturbation not only of Kerr black hole, but of generic type D metrics, you will find some type of Hoyne differential equation. But let's keep with our Tukhowsky equation. So we want to be able to somehow rewrite this infinite sum of MST coefficients. And for that, we use the technology that you guys know, probably Nathan more than us, and it's basically it comes from a very simple observation. So this was what we wrote in this paper with the CISA people and Sihan. which is that if you write correlators for irregularly wheeled correlators, you compute the bit set state for those guys. This is basically a differential equation. And in the semi-classical limit, meaning when you take the infinite central charge limit or the zero Libby coupling constant, that differential equation becomes exactly the Hoyne differential equation. So the Hoyne differential equation, then you can map to the Tucholsky equation by certain dictionary, and you could solve that either using conformal block techniques, but you can also use the advantage of the AGT correspondence to relate those, to find like explicit combinatorial expression for those Virasoro conformal blocks in terms of the so-called instanton contribution to the Nekrasov function. So to relate to the Tucholsky equation, you take the confluent limit, and then you will find either a map, a dictionary that relates the black hole parameters to the gauge theory parameters or to the conformal momenta in your CFT. So this is what the solution to the radial Tucholsky equation look like in terms of the Nekrasov function. So this F is the Nekrasov function. And the different M's in there are gauge theory masses, and L, what is it? L here is like an instanton counting parameter. So you can separate the solution to two pieces. So notice first of all that you don't have any infinite sums of n's of MST coefficients in there. You just have very simple functions. So one piece in red, which we call the far zone piece, and one piece in blue, which we call the near zone piece. So the near zone piece it's a function of this kappa function, which is the tidal response function. So that function will capture all of the tidal deformability of the black hole due to the wave perturbation. And it doesn't show up at lower orders in spin. It starts showing up exactly at the fifth order in spin, where you have all of these polygamma functions of the spin in the black hole perturbation theory solutions. So this is the dictionary that relates the gauge theory parameters to the black hole parameters. So kappa here is just the horizon parameter of the curved black hole. M is the azimuthal eigenvalue, and epsilon is just the post-Minkowskian parameter, gm omega with omega, the frequency of the gravitational wave scattering off the curved black hole. So let me, like one of the advantages of writing the solutions of the Tucholsky equation in terms of this function is that you can make like non-perturbative statements. Even though you don't know what is the explicit form of this F, you know what is the non-perturbative definition of that one. And by using that, you can prove several things about the far zone solutions, which I will not show. I'll just enumerate. So as I was telling, the near zone solution doesn't see any finite size effects response from the wave perturbation, so it's like the point particle limit. And you can prove that it is purely elastic, so there is no imaginary contributions in that. So there is no like absorption by the horizon of the black hole. Also, you can prove that the curved black hole horizon parameter, this kappa square root of 1 minus chi squared, never appears in the far zone solution. Therefore, the solution will be always like a polynomial in chi. So, and that aligns very well with the spin multiple expansion that we were discussing before. And finally, this rewriting the solutions of the Tucholsky equation in terms of the Nekrasov function, they naturally they are like a resummation of all of these MST coefficients. So, basically, this MST coefficient, they are always like have like a PM expansion. So it's natural that you can sort of resum those into some kind of exponential. So, of course, we just check this relation up to, I don't know, like 10 PM orders, and so that it was satisfied. So we conjecture that has to be true all the time. For the near zone, on the other hand, as I was telling you, you have this tidal response function, and they capture finite size effect deformations when you go very, very near to the black hole horizon. So in particular, you see that they scale with this instanton parameter, which in itself scales with G, and A that receives G contributions. So you will have these log G contributions or log omega contributions coming from the tidal response function. So that's like one of the source of this log UP that we were seeing in the gravitational cell force computations. Some of those appear from the fact that you are PM expanding, meaning expanding in powers of G this factor. This factor, it just comes from the connection formula. Yeah, this is called finite size deformations of the black hole, like tidal deformation. But those tidal deformation will be dynamical. Because I'm going to show you how to match to I'll probably not show you, I'll mention that the operators that you can write in a Compton amplitude, they are quadratic in Riemann. And those one will naturally match those finite size deformation. Some of them will be zero because of the zero love number for the static zero love number, but some of them will be non-zero, and they come precisely from this. Yeah, of course. They are Riemann and fifth order in spin, for instance, right? But derivatives of Riemann, because they have to be dynamical, right? Exactly. So you have 4 Riemanns, two copies of Riemann, one derivative at least, and many indices that you can contract with spin. So unlike the far zone, the near zone is not conservative. It has absorption. It's the fact that you are just at some point have this kappa scale basically with omega. So when omega is small enough, you will such a wavelength will be absorbed by the black hole. And that happens exactly at the fifth order in spin 2. So you can. Those happens as dynamical processes, right? Like what changes is say the masses or the spins of the black hole, but they should come out of the computation, not as an input of the computation. So those deformations will come out too. But we haven't really computed though. I mean, we know that there is some Riemann square operators that are allowed there, but what is the form of deformation? I couldn't tell you exactly what they look like. So also something interesting, which so I will set to 0 absorption first of all. So I'll just remove this eta factor when I compute the solutions of the Tchaikovsky equation. And something that I'm not going to mention, but is very interesting, is that you can find an exact quantization condition for the quasi-normal mode. So basically, when this factor goes to 0, and you can rewrite it in terms of the full partition function for the n equals 2 supersymmetric H theory, so the one loop contribution plus all of the instanton corrections. But I'm not going to talk about that. So okay, so basically, you have this guy. From this guy, you can compute a Compton amplitude, right? And you just have to expand that in spin and in the energies. So, and then you can match that to a covariant amplitude. So, because I want to use that in the triangle, I just want to match the 3-level contributions that come from that solution. And from the far zone, it's very easy to extract those 3-level contributions because the far zone, they are always polynomial. The near zone, it's not easy, so that's why I'm just gonna, instead of trying to collect the 3-level contribution, I'll just collect the contribution that come from the full L equals 2 mode in the partial wave. So what does the covariant amplitude look like? Up to 4th order in spin multiple expansion, they can be just captured by this usual exponential, right? People have seen this exponential before. And the near zone contribution start to show up at 5th order in spin and on. So by the way, this exponential of the fourth order spin you can recover with the spin multiple operators that are linear in Riemann, meaning that they don't have anything to do with tidal deformations of the black hole. So then you want to introduce a higher spin contribution both from the far zone and the near zone, so you have to correct this exponential introducing contact operators. And those contact operators, you can write it in terms of this spin basis. So you have three spin degrees of freedom, which you can just parameterize with these three guys. So this K you can think of as the momentum of the incoming wave, K3 as the momentum of the outgoing wave, and W as some massless vector form with the spinors from these two guys. So at spin to the fourth, you can write some tidal deformations using this basis. And those tidal deformations, if you write a word line and compute where those are, they are, as I was telling you, quadratic in Riemann. But because you do not observe any tidal deformation from the Tykowski solution, so the coefficients of those ones should be 0. So that's basically, there is no contact term at spin to the 4 because the vanishing of the love numbers for Kerr. At fifth order in a spin, you can write this guy. So Z here is just like an operator proportional to two spin guys, just to complete the fifth. And you have you can have an answer for that in terms of two free coefficients, C30 and C31. Oh, that's the S channel pole. So it's just like the momentum of the incoming minus or plus the momentum of the incoming massive guy with the momentum of the incoming massless guy square. No. This is just the S channel pole. It's kinematics, not spin. So if I impose that at this ordering spin, I match the Tykowski solutions, I get, first of all, two terms that come polynomial in spin that cancel between the far zone and the near zone contribution. And then those additional polygamma contribution and log kappa contributions that you can encapsulate in just one number, right? There is the appearance of this log epsilon or log p guy, and this has a very interesting story which I'm not going to tell, and that's basically appeared because this effective operator that you write in your effective action, they run, so they control the run of those operators. So okay, I fix the coefficients in my Compton amplitude, which means I can compute the scattering angle, which means I can compute the Hamiltonian, and then I can compute observables, right? So for instance, if you compute the redshift, you get a contribution of this form at that order in the PN expansion. Yeah, but this is just a number. Like the spin of the spin parameter. No, it's okay. That's a good point. So it's polynomial in the spin multiple expansion in A over B, but K is not a spin multiple object. It is A over GM. So K, the expansion in K is not equal to the spin multiple expansion. It's a different expansion. And in particular, for Kerr black hole, this is just a number. So I can just capture it in an ansatz. Okay, so you compute observable, and then you try to compare to what people have computed in the Salesforce community. So this is I showed you the eccentricity square result. Now I'm just picking up the eccentricity 0 result, computed by Chris and collaborators back in 2016. Which basically I want to look at so Y here is like the UP that we were discussing before, and Q is like K for us. So first of all, you see that the polynomial piece you can naturally capture by these 16 times 3 over 20 from our solutions because the polynomial piece cancels from this one. And on top of that, you can capture in the C's some of the polygammas and the log kappa contribution that come exactly in spin. chi to the 1 and chi to the 3 solutions in the gravitational self-force computation. There are some additional contributions that come out from matching the Tykowski computation, which match some of those extra pieces. So, in summary, like, okay, up to spin to the 3 and 4, we fix those guys. At spin to the 5 and spin to the 6, you can write analogous answers for the scattering angle. And those scattering angle coefficient, you can fix it from solutions of the Tykowski equation, this free coefficient that we matched there. And there could be 3 prescriptions that you could take to say, okay, this is the final spin to the 5th Hamiltonian. If you want, you can either keep everything, capturing tidal deformations of the Kerr black hole. You could do a small spin expansion, which is small expansion in Chi, but that's different from the spin multiple expansion. And you will get like these non-rational numbers that come from those polygamma functions, which sort of will hint that in such a type of expansion, those polygammas are like kind of loop expansion in a Feynman diagram computation. Or you could match just the polynomial guy. I prefer to match everything because that captures all of the tidal deformability effects of the Kerr black hole, and the polygammas and everything appear in there. At spin to the 6, there is an accident, which is that for aligned spins, all of the polygamma contributions, polygammas in spin, they cancel each other. And then you get just a rational contribution for the Tykowski solutions, and you can match those. It's very easy to do. So, okay, I'm just going to flash. Once you have fixed the Hamiltonian, you can compute observables for, say, redshift for eccentric orbits. So these are guys at all orders in the eccentricity parameter that you can find in our paper. For redshift or spin precession frequencies, you can find those in there as well. So let me just stop here and summarize. So we have successfully used the diffruting method to study spin to the 3 and spin to the 4. Dynamics leaving a free coefficient. We use black hole perturbation theory solution to compute Compton amplitudes to introduce spin to the 5 and spin to the 6 effects. You can capture finite size effects from the near zone physics and provide explicit results for redshift and precession frequency observables for generic eccentricity in the black hole. So, thanks.
Aside from comparing with what other people, so it reminds me of like 7 loops of triangular computation. People compute it because other people are computing, and then you try to compare to see if you compute it better. Is there an application beyond?
Yeah. This goes directly into the waveforms, in the pipelines for computing waveforms, right? Well, the advantage of this guy is that it's analytic, right? So if you have a wave template, you can evaluate it very fast because you can just evaluate the parameters very fast.
Yeah, I'm not
And
saying they can't do that. I'm asking, does anybody do it? Does anybody plug these?
not yet, because these are new guys. I mean, the old ones, they are already plugged, like Chris's results and everything. They are already plugged in. Those were like circular orbit results. They are already in the pipeline. So these ones which come with eccentricity, they are not relevant for LIGO, but they will become relevant for LISA, right? So if you compute 10 years. Well, but this is the first step towards.
Whenever we see eccentric mergers, eccentric spiral, this would be considered for the dynamics of the wave.
No, I'm not saying this, something like this won't be relevant, but I expect in 10 years, the other papers, the other things that are being done.
Okay, but then we'll have to compare with our results, right? Yeah.
Well, who knows?
I mean, unless you prove that this is wrong, this would be extended.
No, but, okay, but again, I'm not in the field. You tell me it's not true, I believe you, but you're doing analytic computation, right?
Yes.
I assume the computers can do this also.
No. Computers can do for
Oh, no, no, of course, analytic is much more understanding. But in the end, what's going to go into the waveform is most accurate, might not the most accurate.
Yeah, but I mean, the numerics can cover the full parameter space. So what we use are chronological waveforms that hold in the analytic information and complete it with the numerics.
Yes.
But
This I
you need an
understand.
analytic answer.
Okay, okay, anyway. So at this point, there's no place to put this into the experiment, is that fair?
Because doing
No.
eccentric searches is too hard at the moment, and is not necessary for for second generation.
Yes.
But at some point, people will see eccentric waveforms. So, of course, people are already discussing, there are already a lot of efforts to build eccentric waveforms, but they are still at preliminary level.
Yep.
They have been built. I mean, you can find on the web eccentric packages, Python packages producing eccentric waveforms, but they're not used for.
Like
The analytic computations that are used today in the waveform come from when? What's the most advanced? I'm just trying to understand.
most of them, they come from PN literature, from PN results. Like, no. Oh, from PN, I said from, not for, from PN computations. So even all of these PM results that people discuss, there is huge community on those ones. Those are not even used yet. Like everything that is used by LIGO so far is produced like last century. If you want.
No. I mean, 4PN is available since 10 years.
Oh, okay.
It's in the waveform now. 4PN.
Okay, then.
10 years ago was found. Basically, when I moved here,
Yeah, but that was not using this amplitude machinery yet. That was solving.
Yes. No, folding in the PM information into waveform, it's a bit more involved. Yeah. It's less straightforward. I mean, folding in PN information in waveform is straightforward. You just type the number into the code. Folding in PM information requires some machinery that is not quite automatic yet.
I mean, at some point it will become relevant.
Yeah.
Either by people extending it or not, but I think it's good to understand it at this moment. If we can understand it, why not?
You mentioned very briefly, you said that you didn't want to get in the subject, but you mentioned the quasi-normal mode.
Yes.
That your results give some information about that.
Yeah, well, basically the quasi-normal modes, you just want to see what are the points in which the scattering amplitude blow up, right? And those are exactly, well, probably you can just see it from, the scattering amplitude is basically controlled by this guy, so you just want to see where these guys become zero.
So this gives you some information about the merger and what's called...
Where this is zero, that will give you what are the frequencies at which this expression explodes. And say you can, in the end of the day, you're going to relate those quasi-normal modes to the solutions of the Tukowski equation. That's what people usually do. It's only that they will give you like an analytic expression for those quasi-normal modes. Usually people just solve this equation numerically, but you have like an analytic quasi-normal mode condition. We were not the first one to invent that. This has been there for at least 5 years. And people then compare to the numerical result and see very good agreement between the quasi-normal modes as predicted from here or solving them numerically from the beginning.
Thank you.
So does everybody agree? I mean, sometimes the most interesting thing is when people don't agree. Does everybody agree with all these computations, or is there controversy in the literature? Or?
No. These guys. This is just a new way of doing black hole perturbation theory. The old way was just doing this infinite sum of MST coefficients. This is a very nice resummation of those coefficients. This is a technology that is being used a lot nowadays, not only for Kerr black hole, people usually to compute quasi-normal modes, excitations of other kind of exotic objects.
So everybody agrees, so people using different technology agree with the same
Yes.
answer?
Yes, definitely.
For the moment, it's uncontroversial.
Yeah. Okay.
But it provides advantage from this one because you can make statements about the properties of the amplitude that you could not make with the MST solution.
Okay.
So if I may just make a comment, because we're talking about simulations versus analytic solutions, and whenever I try to do solving an equation numerically or making a simulation, it was very nice to have some ground-based problem that I knew analytically to contrast, to make a proof. So in that sense, anything that comes numerically after the analytic solutions is some extension of the thing. I'm just commenting, adding some motivation for the analytic solutions. I think it's very useful to have something analytical when you're doing numerical to compare. Like, are we doing something correct? Because a numerical simulation, it's kind of black box. We don't know what's doing, what it is doing.
Yeah, definitely. I mean, at some point I was talking to Martin, where he was asking, okay, what is the advantage of rewriting the solution of the Kolsky equation in terms of this Nekrasov function? If you want to do numerics, right? So they can do, say, MST numerics very fast, but they have problems when it comes to this A parameter, which people call it like a renormalized angular momentum. Yeah. And it's that this guy, in the low frequency region, it looks real. In the very high frequency region, it looks imaginary. Yeah. But there's some intermediate region in which it's like complex. Yeah. And people doing analytics, numerics do not have too much control on that. And he was asking me, okay, can rewriting that in terms of F gives you like a better understanding in these intermediate regions? And the answer is, I don't know yet. but it's interesting that it's there.
Last year or 2 years ago, there was a meeting we had, and there was some confusion about gauge invariance or something like that. That's all been resolved, or?
No, but that problem still holds. No, the problem ISP.
No, but that problem was different because the problem was that you wanted to match black hole perturbation theory solution in an unphysical region, which was the super extremal region, which was basically re-expanding these polygamma functions, not in the re-expanding these guys in the super extremal spin region for the black hole, and there was some controversy because they have discontinuities when you do that analytic expansion, and people that were also questioning, do this really describe the black hole or not? So the new approach that we take is like we never expand in super extremal region. We keep the physical region and capture everything, and that everything gives you just the tidal deformability of the black hole, the physical black hole. People still want to find a 3-level amplitude. In my case, I don't. So I'm fine with just capturing.
Sorry, I don't know what physical means versus super extremal. What's it there?
Yes. That's that was the controversy. Yeah.